It was definitely a challenge. In fact, I'm going to be honest, I didn't solve it. I used someone else's solution. But you still learn something. If you're not able to solve a problem, I still recommend, just it's better to just find out another solution, and go through it yourself. Make sure you understand something. That probably is a better way to learn than just doing problems that only you understand. So today I'm trying to set a good example. But we have 3097 for today's daily. Shortest subarray with or at least k, 2. You are given an array nums of non-negative integers and integer k. An array is called special if the bitwise or of all of its elements is at least k. Return the length of the shortest special non-empty subarray of nums, or return -1 if no special subarray exists. So you're trying to find, so a subarray being a contiguous array within the array. So there are some hints, and the hints actually very much pointing towards the best solution, pointing out how there's 32 bits and everything. And so my solution came 4 test cases away from working, but it actually exceeded the memory limit. Yeah, that's right, 714 out of 718. So it did work, but let's go through it and see why it why it used up all the memory. So my idea was that you could save time by, instead of recalculating the or sum every single time, just basically keeping track of the last or sum and then just tacking on the newest value. So if you have like 1, 2, 3, 4, well, you calculate everything, all of the subarrays that end with 1. All right, so you get 1 for that. Then you calculate all of the subarrays that end with 2. So you either have 1, 2, which is 3, and then you just have 2, which is 2. And then you have 3. So now you have 1, 2, and 3, 2, 3, and 3, and so on. And that makes a 2D array where each row is 1 longer than the last, because now you have all of the prior subarrays plus the newest value. And then once you assemble that subarray, well, that 2D array, you just go through it, and I have this little based on the indices of the subarray, you're able to check if you're able to find the length of the subarray that added up to that sum. So where I points to the row being where the row is all the values that end with, where the row value points to the array with all of the array values, with all of the subarray sums that end with that value, and J is the values within that. So as you go through J, you use up less and less elements. So the further you are along J, the smaller the subarray gets. Because remember, the first value is every value up to the end point that you're on, and then the last value is just that end point. So a little counterintuitive, a little backwards, but actually kind of elegant. So fairly happy with that. And then you just calculate the min subarray by calculating that difference between the two indices, because if J is really big, then that means that you've gone all the way through the row, and if it still is greater than K, then that means that then that means that it's a small subarray that's big enough, and so that is the new contender for the minimum, and then you just add 1 to account for the 0 index of the indices. Now that works, but it 714 cases, but not enough. You need it to work for all of them because this is too memory intensive. So major thank you to Bijoy Singh for this very good solution and for writing it in all the languages. But really admire you doing this, and I am going to try my best to explain what you're doing. And it's and I appreciate it because I feel like I learned something as a result. So we're going to revert the code to this result right here. Okay, and here we go. So let's look at the hints and see what we learned from them. For each nums I, we can maintain each subarray's bitwise OR result ending with it. The property of bitwise OR is that it never unsets any bits. It only sets new bits. And so the number of different results for each nums I is at most the number of bits 32. This is a little bit of a red herring. We can maintain each subarray's bitwise OR ending with it. That doesn't mean we should, because as we saw, when we did that, even though we did it as efficiently as we could by only tacking on each new value as opposed to calculating the whole thing, the problem is that we use up a huge chunk of data maintaining all those values, because the array can get really big, as you can see, and that means that you're maintaining ON squared values in that subarray. Well, in that 2D array. That's just too big. Rare to deal with a memory problem in LeetCode compared to a time efficiency issue. I did have one idea, which was to basically cap how big each row can be. Because, like, let's say you go through a row and you realize that, oh, wait, this subarray is only length of 5, but it's greater than k. That means that you never need to calculate the sum of any subarray with a length greater than 5. Or actually, even then, or even equal to 5. Because you found 5, that's your new minimum. Let's just see if we can get something smaller than that. So that would theoretically shrink it, but of course the test cases are written very well. And if you have inputs where the array is really large, but you also require all of those values, then that cap is never going to come into play. So that's the issue with that. So what do we do here? Well, this is a fantastic solution. I love it. What we do is we have an array that keeps track of all the bits, and there can only be 32 bits. It's based on the constraints and it being an unsigned integer. And what we're doing is a sliding window approach, which is one of the topics. So of course that makes sense. And what we're doing is we're calculating a subarray sum, and we shift right. And then we try to see, and if that subarray adds up to k at least, then we try to move in from the left. So like we have like this. Okay, so let's say we're looking at these first 5 digits, and we're representing the ones that we're counting in the subarray with ones, and the ones that we're not counting with zeros. So we start by saying, okay, so let's try just the first one. We get nothing. Well, that's not bigger than k. Okay, so add the second one. That's not bigger than k. Okay, add the third one. That's not bigger than k. And then add the fourth one. And finally, the fifth one. Finally, that's greater than k. So what do? Now we try to see how much fat we can cut off. Because remember, it has to be contiguous. So we can't get rid of any of these middle values. So now we get rid of that first value. And we say, hey, is that greater than or equal to k? And if it is, then we try getting rid of the second value, and so on. Once it's not big enough, then we go back to adding. Okay? And that, beautifully intuitive, actually. It's gorgeous. It's hard to derive that solution, but the solution itself makes perfect sense. And here's how this specific user did it. So what they do is they loop through all of the right endpoints, and they keep track of the current OR being the total value of all of the subarray sums, so that instead of having to calculate the whole thing, you can just tack on the last value. All right, and then what they're going to do is they're going to go through all the bits, and this is where it gets really clever. These bits are not just ones and zeros, but rather the counts of each of set bits for that point. So they don't just cap at 1. It's not just yes or no. It's if there's 5 bits, if there's 5 numbers that have that first bit, then that value is going to be 5. And that's useful because later on what we can do is we can say, okay, well, let's get rid of those numbers. And when you get rid of those numbers, you decrement those bits. And when you decrement those bits, if you as long as you don't hit 0, that bit is still fine. But if it's once it hits 0, then that means that no number has that bit. And you can use that to calculate k, and remove values. Because the problem is there's no... How do you take out an OR? Like, how do you do that? Because OR, you have like 1, 0, and you could have 1, 1. Well, that makes 1, 1. Well, now let's say on paper that we subtract 1, 0. Well, that answer is still 1, 1, but I can't really think of an elegant way of subtracting that, like, with XOR or AND or something. There's not really a way because you don't really know what that added to the equation. If you only had the sum, you don't know what a specific number added to the equation. Did it add this bit, or were there 5 other numbers that added that bit? So by keeping track of how many bits are each number added, then you can elegantly remove it. So we go through all of the right endpoints of the array, and we keep track of the current subarray sum. And now what we're going to do is we're going to go through all what that number brings to the equation. So it's like, okay, well, we're taking on this newcomer, this right value, and we go through that array, and we say, okay, well, it adds, the first bit is yes, so tick that one up by 1. The third bit is a yes, so tick that one up by 1, and so on. So then we'll have a count of all those, of the number of numbers that have each bit at each index. Now, this is done really well. We have 2 things. First, we check that left is greater than right, because we have the right point, but we also have the left point, because remember, we're trying to shift in that left point as much as we can go while it's still being greater than or equal to k. So now that we've set this new right, we're going to try to inch in left until left either hits right, in which case that's 1, or current OR is less than k, meaning, oh, we've gone too far, we've chopped off too much. So if that is true, then if that is true, if the current OR is greater than or equal to k, then we're going to set that new minimum length if those new bounds are less than or equal to the current king of the minimum length. And then we're going to update OR by removing the left values bits. This is really cool. So you go through all those bits and you say, okay, well, we had the leftmost value in this subarray. All right, so let's go through all of its bits by using bit masking, and we're going to shift up bit. So we start with 1, and so by bit masking, by ANDing a value with just like 1 bit, we can isolate those that 1 bit. So for example, if we have like like this number right here, 1, 2, 3, 4, 5, what's a quick way of seeing if the first bit is a 1? Well, we could just AND it with another number where we know it's just 1. So that would return 1. And so we're saying, okay, so if there is a bit there, then remove it from the array. Or not remove it, decrement it. So now there's 1 fewer number that has that bit. What we do is we reset the recalculated OR to be 0. And what we're doing is we decrement them, and then if it's still greater than 0, then we throw it back in. So every number needs to be evaluated. Every bit needs to be evaluated. So it's like, okay, well, is this bit still in play? Well, what if we got rid of the last number? Okay, well, is it still in play? If so, throw it back in. So each bit has to earn its way back into the number. Then we just reset that to the current OR, and then we shift in left once again. We're like, well, let's see if we can get rid of another number and it's still greater than k, because we want to go for the smallest subarray possible. And yeah, so by keep on doing that and then going through all the subarrays, I think that maybe this should have I'm not the expert because someone else wrote this, but I think that maybe this could, actually, I don't think it would be that efficient. to I was thinking maybe like if this condition was met, then you can't have a smaller subarray than that. So you could have one check that's like, well, check to see if left is now equal to right, because if left is equal to right, then you found a subarray length of 1 that's greater than or equal to k. But the problem is that's an even trade-off, because now you're adding one more check for every single loop, as opposed to just going through the loop and just seeing what happens. So it's situational. In some situations that could be good, in other situations it's just wasting time. But then once you go through that entire loop, now you just check to see if that minimum length is not still the maximum. So that will only happen if it's never going to be greater than or equal to k. And if that's never happened, then you return 1. Otherwise, you return whatever the minimum length was set by this line. Fantastic solution. Great job. Thank you so much once again to Bejoy Singh. Thank you so much. That is a fantastic solution, and I very much learned something because of it. I hope I explained it well. And yeah, I know I didn't write the solution, but I feel like explaining things and figuring out how to interpret them in such a way that I can explain them is a great way for me to learn. So thank you so much, and you have a great day, everyone.